So welcome to functional programming, destination or origin. And my thesis is that functional programming is at least as good a launching off point for other paradigms as it is a goal to achieve as a paradigm in itself. So what that makes me focus on is what I consider to be, yes?
Could you introduce yourself, please?
Oh, sorry. My name's Paul Snively. Not that it matters, but I work for Verizon Labs, and my day job is in Scala, which is super cool. And guess what? There's no Scala in this presentation. Right? Yeah. So I get to talk about other cool stuff, which is nice. So anyway, launching off point, functional programming. I'm taking that as a launching off point, not a destination. So what is the essence of functional programming? The essence of functional programming. The Kleisli category for any monad, for any category C, consists of the objects in the Kleisli category are the objects in the category that your monad is in. Your homomorphisms from the category to the Kleisli category are the homomorphisms from the underlying category to the monad constructed from the underlying. Do I see a hand? No. Okay. Let's see. The identity morphism in the category with your monad is simply the eta of the homomorphisms from X to X in the underlying category. And the composition, function composition, what you would otherwise call function composition, is Kleisli composition F to G, G to H, is again just the monadic functions from the underlying category. And the Kleisli category is a category for these reasons, for the standard reasons. And again, I assume everybody knows this. Just kidding. So what is this Kleisli business? And what is Kleisli composition? What is the Kleisli category? Michael O. Church, I think, has given the best explanation of this. That what's great about the Kleisli arrow is that it gives you the purely functional view of what everybody else means by a function. In particular, an impure function, a function that does other stuff, while it is in the process of returning a result. But also makes explicit that what is going on in a monad. And more from Michael O. Church. It makes clear, especially notationally, if you sort of group the M in A to MB, which is how you normally express a monadic function. If you think of the M as being associated with the arrow, as opposed to with the return type, that I think, and Michael O. Church thinks, and I agree with him, that nicely captures this notion of monadic context or computational context. It associates it with the arrow instead of with the return type. And so an A to MB is just like an A to B that happens to do M stuff as well, okay? And normally, especially if you're new to functional programming and monads, you probably think in terms of this computational context or monadic computation as being how you do stuff like I/O and how you manipulate state and all this kind of stuff. One of the points I want to make is that this notion of computational context is much richer than that. Okay, logic programming. I'm going to move really, really quickly. Please don't hesitate to interrupt and ask questions, but ideally I'd like to save the questions for the end. I want to leave as much discussion time as possible. Logic programming, okay. This is a little scheme program using microcameron. It's a little stylized in its typography, but basically this says you can define A and B as the conjunction of an expression that takes a logic variable, in this case A, fresh, call fresh means call with a fresh logic variable, lambda A, unify A with 7, the equal, the triple bar equal just means unify. Call fresh lambda B with a disjunction of unify B with, what do we have? Unify B with 5 and unify B with 6. And if you run that program, that logic program, on the empty state, you have to give it an empty state, you get two answers. one that binds variable 0, that's what this means. The variables turn into these sort of numbered, indexed things. One that binds the first logic variable with 7 and the second logic variable with 5, and then and this is a counter indicating what the next available logic variable is. Don't worry about that. And another answer that again binds the first logic variable with 7, but this time binds the second logic variable with 6. And what this basically means is these are just lambdas. These are just ordinary functions in Scheme. And so somehow we have contrived to create functions that return more than once, right? That return more than one result. So there's some sort of backtracking going on here. How does that work? Okay, here is the essence of logic programming. This is a little bit of the implementation of microcanron in Scheme, R6RS Scheme, standard R6RS Scheme. And basically we have the triple equal thing, and all it really does is say, try to unify this thing, and I didn't have room on the slide to include the source code for unify. Unify just takes one set of variables, another set of variables, and says, are they consistent with each other? So including things like one side says x equals y, the other side says y equals 2, so now you can say x equals 2 once they're unified, right? And then you have a definition of unit, and a definition of M0, and disjunction, conjunction, this funny thing called M+, and this funny thing called bind. Now, you're at LambdaConf, right? You've probably now been to several sessions where you've heard about bind, and you've heard about unit, at the very least. The M in M0 and M+ means exactly what you think it means. So this is actually just an implementation of what's called monad plus in Scheme, and all it's really doing, the only thing that's really sort of interesting here, I mean, disjunction and conjunction are probably pretty familiar. M+, what monad plus does is it lets you say this thing or that thing. That's essentially what M+ does. So this or that. And so you're almost at disjunction already, right? And then M0 is just no, there's nothing, you didn't get a result. And so this is an M+ monad for logic programming. And the entire implementation of microcanron, by the way, is 39 lines of Scheme. So if you ever wanted to see the smallest, I think, likely the smallest implementation of logic programming, microcanron is a really good place to look. And this, obviously, is not doing I/O, it's not doing state, it's not mutating anything. It's just using a monad, it's using a particular kind of monad to implement a backtracking, fair logic programming system in 39 lines of Scheme, not all of which are on this slide. So here's an example of where computational context lets you implement this notion of functions that return more than one result, which is central to logic programming and has nothing to do with I/O or state. And here's a little quote from the paper that microcanron comes from, where they talk about exactly how they model partial functions, functions that can fail. What do you want to do when the function fails? You want to try again. You want to try to come up with some other answer. And so here's a little bit of admittedly deep, dense explanation as to how a partial function can model a logical relation, okay? And in the interest of time, I'm not going to break this down. I really just want to offer it as an example, and I encourage you to read the paper itself and play with microcanron. Download Shea Scheme, download microcanron, take it for a spin. It's really a lot of fun if you haven't played with logic programming before. So again, the focus here is computational context. What is the breadth of the meaning of computational context? Again, M0 and M+ mean exactly what you think. Monads carry the computational context through from function to function. That's how they're different from applicatives, that's how they're different from pure functions, right? Monads actually take a context, take a computational context, and then propagate that computational context through from function to function. That's how they're different from pure functions, that's how they're different from applicatives. Obviously, computational context you've heard a lot about, I/O, state, concurrency. Monad plus here is capturing the notion of partiality, is capturing the idea that a function might not return a result, and you might want to do something besides just go bleh, you know. And monads revealed. One of the other things I really like about the microcanron source code, all 39 lines of it, is that it makes super crystal clear that monads are just a particular pattern of use of higher order functions. There's nothing remotely mysterious about them, once you know the monad laws. There are only 3 of them, guys, come on. Probabilistic programming. Okay. This is a popular example in the probabilistic programming literature. It basically asks the question, what's the probability that it's raining given that the grass is wet? And it could be wet because it rained, could be wet because the sprinkler was on, all that. This is just a little piece of OCaml code, very simple program. And we start by defining a flip function that basically takes a probability and then says, you know, that thing's either true or false. So whatever probability it's passed, then the opposite is whatever is left when you subtract it from 1, right? That funny syntax, that's 1 dot minus dot, because floating point subtraction in OCaml requires you to include the dot. And here's the probabilistic model where we basically say what's the probability that it's cloudy, what's the probability that it's raining given that it's cloudy or not cloudy, what's the probability that the sprinkler was on, what's the probability that the grass is wet, and so on. And then we ask the question, what's the probability of rain given that we have wet grass? And what else is interesting about this? Oh, right, when we actually run it, and then there's a little function normalize that just makes sure that the probabilities sum up to 1. That's all that's going on there. So the probability that it's raining, given that the grass is wet, is 0.7079, et cetera, et cetera, et cetera. What's interesting about this is that this is plain old OCaml code. So there's some really funny stuff going on in here, like it's asking, like we're using if, a Boolean expression, with something that doesn't seem to be a Boolean, like these probabilities don't seem to be Booleans, right? So how does that work? Well, here's one way, given that this is an embedded domain-specific language for probabilistic programming, here's an implementation of it using monads. And we have this type, PM stands for probability monad, and that's, in this implementation, just defined in terms of a lazy search tree called PV. Again, I didn't include the source code for that here because it doesn't fit in the slide, and it's not really the point. The point is that this is pretty ugly. That's actually the point. You can do this. You can define everything in terms of a probability monad. And by the way, what does this domain-specific language do, right? So first of all, you can construct the probability distribution. That's dist. Of course, you want to be able to say not, or negate. You want to have conjunction. You want to have disjunction. You want to have if. You want to have lambda abstraction. And you want to have function application, right? That's what all of these things are intended to do. I'll be very impressed if you can make sense of this code. You know, I can barely make sense of this code, and I've been programming in OCaml for over 15 years. But you can do that with monads, and you can write client code using this implementation. It won't be as nice as the code you just saw. I'll explain how to solve that in a minute. But stochastic functions, Oleg Kislyak and Cheng-Chia Shan have basically said, to try to tie this back to the logic programming a little bit, again, the key thing is how you write functions that return more than once. And that's something you can do with, given that you have access to the computational context. And again, monads are one way to do that. We just saw how ugly that can look. Here's another implementation of the same module in OCaml, and it's the one that actually you use to write the type of code that we saw in the earlier slide. And what's going on here is basically all the types fall out. Our probability monad for A is just A. There's no more monad. The arrow type representing functions from A to B is just A to B. The constructor that lets us build a value of X is just X. And dist is kind of interesting because now we have this funny thing called shift, and all of a sudden now there's this function that just magically takes a k, and that's the continuation. Because it can't be c, of course, because c is the speed of light. So this is where this notion called delimited continuations comes in. Shift says, give me whatever the current computational context is. The continuation of your program is another way to say the computational context of your program. Like when you get an exception and you get a stack trace and it shows you where the exception occurred and all that kind of stuff, the dirty little secret is it also tells you where your computation would have gone if the exception hadn't been thrown, right? So this is very similar. It's just deliberately asking, give me the stack, or give me part of the stack. It's delimited continuation. So this says, give me where I am, and then let me go ahead and build this probability distribution. And oh, by the way, when it turns out that whatever thing with probability x turns out not to hold, then go ahead and call the continuation and do something else, make another choice. So negation becomes simply not. Conjunction becomes and, disjunction becomes or, if becomes if. Lambda E is just E, application of E1 to E2 is just E1 applied to E2. Everything is direct. And then you run this thing with this thing, and the reset is the other end of the delimited continuation. It's the thing that puts a marker in the stack and says, we're going to backtrack up to here when we invoke this continuation here. So when you have a probability distribution and you need to make a different choice, it goes back to this guy and then continues from there. And that's how you get functions that can be executed more than once in different computational contexts. And that's how probabilistic programming can be embedded in OCaml. One way. Okay, so takeaways. I'm really running through this. I hope you folks have lots of questions. Computational context is an unbelievably powerful general idea. And it's way more important than just dealing with state and I/O in functional programming. Monads provide one way to represent computational context, and they're the easy one to get at because you have monads in Scheme, you have monads in JavaScript, you have monads everywhere. The question about monads isn't whether you have them or not. The question is whether your language makes it easy to write your own or not. Delimited continuations are another way to get at computational context. They're harder to get at. They're usually some sort of funky library, sometimes involving native code. One nice thing about OCaml is that they're an OPAM install away. Delimited continuations are. Monads and delimited continuations macro represent each other. If you have monads, you can build delimited continuations. If you have delimited continuations, you can build monads. They are isomorphic. The nice thing about delimited continuations is they let you write embedded DSLs that integrate with the existing syntax of the language, whereas the monadic version, even if you have do syntax or for comprehensions or whatever, it's going to be a little more heavyweight, it's going to be a little more ugly. So the principal thing I want you to take away, though, is the first one, that the notion of computational context gives you a lot more than just state and I/O. You can implement whole new programming paradigms by having this first-class notion of computational context. Resources, I took a bunch of stuff from these links. All the quotes are from these papers, except the second to the last one I didn't take any quotes from, but it's still relevant to understanding probabilistic programming embedded in OCaml. And believe it or not, that's all I got. So we have an hour, so yeah. Sorry? Yep. So, we have lots of time to talk, or you can go see if there's any ice cream left. Questions, comments? Yeah.
The technique using delimited continuations, I assume that would work as well in Haskell or Scholar or whatever.
Absolutely.
It wasn't leveraging something particular to account.
No, not at all. Delimited continuations have been implemented in a whole bunch of different languages. And in Haskell, so it's almost, you're spoiled for choice. because there's the logic T monad transformer, for one thing. And there are delimited continuation monads in Haskell. So it's sort of pick your poison, because there's so many different ways to represent access to the computational context. You have lots of options, and there are probability monads too, and all that kind of stuff. So the question is, how big a detour do you want to take? You could start with Haskell, add the logic T monad transformer, and then implement probabilistic computing on top of the logic T monad transformer, or you can just go straight to a probability monad. Whatever.
Which one do you think is easier in Scala?
Easier in Scala. So the domain-specific probabilistic language in OCaml has been ported to Scala in terms of monads, as opposed to the delimited continuation plugin, which is not being maintained anymore. I guess with 4 comprehensions, it's not that ugly. It's not that bad. Anything else? Comments, questions? Come on, folks. Don't be shy.
In Scala, I guess I've heard of the async, I don't know if it's a macro or something, as a kind of a successor to the delimited continuation plugin. But then I guess I've been wondering about that because there's also the effectful macro, which accomplishes something similar, but just kind of desugars to flat map calls. So it's
Right.
I don't know. I guess they can both be used for the same effect in general, but they're just implemented in different ways. Like one's more of a kind of continuation, and one just is flat map calls.
Yeah, and it's disappointing because the async macro, and I think it is a macro, is not a general delimited continuation macro. So it takes one use case for delimited continuations and says, let's focus on that, which is fair enough, because I think most use cases for delimited continuations probably do have something to do with asynchronicity and functional reactive programming and things like that. There's sort of obvious applications for it. But it's still frustrating and disappointing because delimited continuations are much more general and much richer.
There was a friend of mine using it for something else that wasn't async, but I don't know how he did that. But yeah, I kind of prefer the effectful one because that's kind of like a general. I can use it with anyone.
Yeah, and again, it's like I don't know how helpful it is to have that when you go looking at some of the literature. Like if you want to try to implement a probabilistic embedded domain-specific language in Scala, and you read Oleg's paper or whatever, getting from there to doing that with async or whatever, I think would be a significant stretch, and maybe not even possible. It's just not. It's not a delimited continuation macro. Yeah.
So when at that point where you're saying that monads can be used for carrying computational context, you said applicative functors don't.
Mm-hmm.
I'm wondering, is that, you're still combining values, but is it the fact you don't have this bind operation is the reason, or?
Flat map is different. So applicative functors do have computational context, but it's encapsulated within the applicative functor. It is not passed from applicative to applicative, right?
Okay.
Whereas so in general, monads have to be sequenced, right? Or I should say they sequence. That's what they do.
Yeah.
Whereas applicatives, of course, nobody knows and nobody cares what order, of course, the joker in the deck here is commutative monads, but nobody talks about those. They're like that crazy uncle in the attic that nobody talks about. But yeah, that's the principal difference. It's true that both applicatives and monads deal with computational context.
Right.
Applicatives just encapsulate that within the applicative.
Okay.
Why do you think nobody talks about the uncle in the attic?
About what? Applicative? Oh, about applicative. Commutative monads.
Yeah.
Probably because A, monads already give people hives, and B, because the criteria for whether a monad is commutative or not is somewhat subtle, and generally speaking, it's hard to look at any given monad and determine whether it's commutative or not. And again, it's like, and if you need a commutative monad, then it raises the question as to why you're not looking at applicatives. Why isn't an applicative functor enough? Like what benefit do you get from having a monad that commutes as opposed to having an applicative functor?
I love what you're saying. Just makes me want to find that one example that, meets all the criteria of what you just said.
Right.
That's like,
Yeah, me too. Like, I couldn't name a commutative monad if, put a gun to my head.
oh,
I don't know. I know they exist. Or actually, because I'm an intuitionist constructivist, I'm told they exist, but I don't have a constructive proof. Yeah.
So if delimited continuations are so easily provable to be monads, or at least monad structures, what is the dual of a delimited continuation?
What's the dual of a delimited continuation? Well, it's more that given a delimited continuation, you can implement any monad. Given monads, you can implement delimited continuations. If you have delimited continuations, I mean, what's the dual of a delimited continuation? I suppose the dual of a delimited continuation would be a program where some function is left abstract. So if a delimited continuation gives you access to the computational context, the program as it has run up to that point, then its dual would be a program that is ultimately going to call some function that could potentially return more than once, but we don't know what that function is necessarily yet. So in other words, that sounds like a natural transformation of some kind. It sounds like a polymorphic function because what I'm saying is you don't know what this function is, which is just another way of saying you don't know what its signature is, which means its argument type is left abstract and its return type is whatever the whole in the program up to that point requires, I guess, if you want to look at it that way. So that's interesting because in the context of languages like Agda or proof assistants like Coq or dependently typed language like Idris, there is this notion of programming with holes. We basically have not yet fleshed out. It's like you're trying to prove something or you're trying to write some function. You don't even know what that is yet, but you can continue to develop your program up to the point where there's this hole. And then, for example, in Idris, you can ask for it to automatically try to synthesize something to put in that hole and so on and so forth. That, I think, is the dual of a delimited continuation.
Okay.
If that makes any sense at all. And don't quote me on that, but that's what comes to mind.
There's actually, I believe his name is Thomas Patrusek, is actually doing some really interesting research on co-effects.
Mm-hmm.
And that sounds a lot like what you're asking about, like the dual of a continuation.
Right. Right.
The way he represents a co-effect is like the programming environment is a co-monad from which you can extract things. And
Yep.
so if you have like a program that has some free variables that aren't defined yet,
Right.
instead of saying, this is an A-mirror, this is undefined,
Yeah.
it says if you can provide definitions for these things, then I can give you the program.
Right. Yeah, and it's also interesting to observe that one of the things that didn't come up here and doesn't come up in the example code that I used, but the delimited continuation implementation for OCaml does in fact support answer type polymorphism. So that's really deep stuff. Basically, you're saying your continuation can go different places. You can return multiple times to different places in your program that expect different types, and that's a pretty remarkable, pretty remarkable feat. Anything else?
Here,
Oh yeah.
can you speak at all to the relative expressive power between delimited continuations and just more traditional non-delimited?
Yep, undelimited continuations, yeah. Oleg Kiselyov, who is apparently here in spirit, has written an excellent post on that very question, criticizing undelimited continuations because they're not functions. Basically, the type of an undelimited continuation is, x to bottom, right? Because an undelimited continuation basically runs off the end of the world. Yeah. So in Scheme famously has continuations, right? Has since 1975. And when you call a continuation in Scheme, it executes the rest of your program all the way until the program terminates, and God knows what happens, right? Whereas a delimited continuation, you're explicitly saying, give me this much of my call stack, and then you can return multiple times to the point at which that is delimited. And with what type? Well, again, it depends upon what type is expected at that point. With answer type polymorphism, it can be any type you want, but it is a function. It is a it is a total function from one type to another. An undelimited continuation is not. So strictly speaking, by the Curry-Howard isomorphism, an undelimited continuation is logically inconsistent, for what that's worth. Anything else? I guess not. Okay. Thanks, everyone.